the biggest passenger plane the world has ever seen.
When you see that huge monster, impossible that this big thing is gonna fly. No way.
It's cutting-edge aerospace engineering.
A massive fly-by-wire system like this is an incredible tool of safety for the aircraft itself.
And the pioneering historic innovations.
What an incredible sensation!
Cayley was the first person to recognize the important forces that are fundamental to understanding flight.
That made the impossible possible. Since the birth of aviation a century ago, air travel has reached monumental proportions. Now, over 3 billion passenger journeys are taken each year. That's the equivalent of half the world's population taking to the skies. With terminals overrun and runways congested to breaking point, aerospace engineers are looking for solutions.
15, 20, 30 years ago, the challenge in the aeronautical field was mainly speed. Then the new objective of Airbus, Boeing, for example, was the size of the aircraft.
In order to reduce the 100,000 daily flights across the globe, aircraft designers would need to think big. And in 2007, what they came up with would smash aviation records. This is an Airbus A380, an ultra-high-capacity airliner and the largest passenger plane on the planet. An aircraft so big that Air France have had to create a giant cutting-edge building just to accommodate it.
We built that brand new hangar to welcome that huge monster, that huge aircraft, so big that our hangars couldn't fit that kind of aircraft.
This revolutionary double-decker plane has an almost 80-meter wingspan, the largest of any commercial aircraft. It has 550 square meters of usable floor space, a massive 40% more than the next largest airliner, allowing it to carry up to 850 passengers. And its mighty turbofan engines and state-of-the-art design mean it can fly non-stop almost halfway around the planet. At its custom-built high-tech hangar in Paris, this Airbus is being stripped back as part of its scheduled 4-year service, revealing the secrets of its engineering success. And for maintenance manager Sylvain Fargo, it never fails to impress.
The first time when I see it, the first word was wow, and it's still wow when I see it. This aircraft was part of what we could call a jump in the aeronautic industry. New technologies required from us to train our mechanics, our engineers, so it's quite a step through future.
The A380 is a colossal feat of engineering that would have once been thought impossible. Man has always dreamt of flying like a bird. But liftoff was not as easy as it looked. 11th century Benedictine monk Almar reportedly strapped wings to his back and launched himself off Malmesbury Abbey.
You're on a man!
But he glided out of control to come to a painful landing. In 18th century Paris, the Montgolfier brothers, noticing that hot air made a paper bag rise, built a hot air balloon and made history with the first ever lighter-than-air manned flight.
Oh, très bien, magnifique.
Although their design did have its drawbacks. But for a flying machine heavier than air to take off and remain airborne, engineers would have to learn how to harness the forces of nature. This would remain an impossible dream. Until, in 1804, British scientist Sir George Cayley closely observed birds and finally unlocked the mystery of flight, earning him the title, the Father of Aeronautics. Cayley discovered that in flight, a bird's wing has a curved shape known as an aerofoil. Air passing over the curved surface speeds up, losing pressure. The pressure of the undisturbed air below remains high, and so creates upward force. Cayley built a whirling arm to test his theories. By turning the aerofoil upside down, aerospace engineer Dr. Ben Evans can demonstrate how this shape can successfully conquer the forces of gravity.
Now, in this experiment, on one side we've got weights representing gravity, the force that needs to be overcome, and on the other end, an aerofoil. And as this spins, the arm goes level. The air passes over the aerofoil and pulls it down to counteract gravity, which is what lift is trying to do in an aircraft, only upside down.
In 1853, at the age of 79, Cayley put these ideas into practice and launched the world's first heavier-than-air manned glider. Sir George Cayley had made the impossible possible.
It's amazing what you get it to do when you know how.
Cayley's achievements have inspired generations of aerospace engineers to reach for the skies.
By doing some very simple experiments, he managed to show what allows a wing to generate lift, just like the wing of this glider that is allowing us to hang here in the skies.
Without the concepts that George Cayley developed, the giant engineering feat of the Airbus A380 would not be possible.
When you see this aircraft so huge, you can say, but impossible that this big thing is gonna fly. No way. But in fact, it's only aerodynamics. The
A380's wings apply the same principles that Cayley exploited, but on an enormous scale. With an almost 80-metre span and a surface area of 845 square metres, they're big enough to park 20 of Cayley's gliders on top. In its custom-built hangar in Paris, this A380 is in for a comprehensive service, allowing technician Charlie Jackson to get up close and personal with these engineering masterpieces.
As this aircraft is taking off down the runway and generating speed, the tips of the wings actually will raise up about 4 meters, which is a sign that the wing is generating the lift that it's going to need to carry such a large aircraft into flight.
To create a wing big enough to generate lift but small enough to minimize drag is a design conundrum. On the A380, special high-lift devices, slats on the front and flaps on the back, allow the wing to increase its size and curve depending on how much lift is required. The wings also maintain the plane's aerodynamic qualities in a more surprising way.
The inside of these wings is the fuel, which you need to complete your flight.
The plane has 11 fuel tanks, 5 in each wing and 1 in the tail. Fuel is stored in the inner tanks to reduce weight at the wing tips. After takeoff, it's pumped to tanks across the whole wing. Throughout flight, the system constantly adjusts the fuel to maintain the centre of gravity.
This wing is the product of good design. If it hadn't been that way, it just wouldn't be practical to make an aircraft that size.
But to create a super jumbo, unlike any other plane in the skies, its designers and engineers would face further major challenges and have to draw on innovations from the past.
What an incredible sensation! I can feel the acceleration pushing me back into my seat.
To produce more impossible engineering. The Airbus A380 is a triumph of 21st century aerospace engineering. The largest commercial airliner in operation today. At its state-of-the-art, custom-built hangar in Paris, this A380 is undergoing its 4-yearly service, allowing admiring technicians to get intimate with this colossal feat of impossible engineering.
It's a big aircraft. You cannot imagine that it's going to go and fly so easily.
But designing a huge plane created huge challenges. Not least how to create engines powerful enough to lift a 369-ton aircraft, plus 200 tons of passengers, fuel and cargo, almost 4 kilometers into the sky.
The engines are one of the most important components on this plane. It's like the heart. It doesn't beat, the body doesn't live.
Getting the A380 airborne would be impossible without the brilliant engineering innovators of the past. By the late 1800s, aviation pioneers recognized the need for power and thrust to obtain flight. In 1874, Frenchman Félix du Temple attached a steam engine to a monoplane.
Et voilà!
But the weight was all too much.
Sacré bleu!
In 1903, American professor Samuel Langley built a giant catapult to aid launch. But the takeoff didn't go as planned. Luckily, 2 siblings from Dayton, Ohio were about to make one of aviation's most significant breakthroughs. In December 1903, Wilbur and Orville Wright launched the maiden flight of the Wright Flyer. Two propellers driven by a piston engine gave the plane enough thrust to take to the air. Although only lasting 12 seconds, covering 36 meters, it was the first controlled powered flight and heralded the birth of modern aviation. However, more than a century on, getting a plane more than 1,500 times heavier than the Wright Flyer airborne would be impossible without a remarkable British innovator. Up until the late 1930s, piston-engine propeller planes had been the aviation standard, but they were limited in range, speed, and altitude. A radical solution was required.
What an incredible sensation!
Aerospace engineer Dr. Ben Evans is experiencing firsthand the power of the Gloucester Meteor, Britain's first ever jet fighter, and impossible without the genius of a British engineer. Frank Whittle, pioneer of the turbojet.
I can feel the acceleration pushing me back into my seat. And these two engines kick into work either side of the aircraft. You feeling okay? Yeah, good.
Whittle's new engines were powerful enough to carry the Gloucester Meteor vast distances at 12,000 metres high and at almost 1,000 kilometres per hour.
This was a leap forward in terms of the possibilities of what aircraft would be capable of doing.
As effective as it was, the concept behind the engineering was deceptively simple.
In essence, the way the jet engine works is you have suck, squeeze, bang, blow. You suck air in at the front here, and then that passes through a spinning compressor. And that compressor squeezes the air down, increases the pressure and the temperature of the air before it passes in to the combustion chamber. Now, this is the point where the fuel is added and ignited. This increases the temperature and the pressure of the gas even further. And then all of those hot exhaust gases have to expand, speed up through the back of the engine, and they pass through this turbine. And the turbine is connected via a shaft down the centre of the engine to the compressor at the front, making that spin. But what pushes the engine forward, what generates the thrust, is the expansion and the acceleration of the exhaust gases out of the nozzle at the back of the engine.
Whittle's turbojet allowed aircraft to fly faster, higher, and further, and changed the face of aviation forever.
So successful was Whittle's design that the jet engine has just become a standard now on modern commercial transport aircraft. The dream of travelling faster, higher, safely, and more economical all over the world became a possibility.
To launch the A380, engineers would need to take Whittle's jet engine and augment its capabilities to an unprecedented level.
That size of aircraft couldn't exist before, so they had to develop and to design brand new engines to suit what's required to have it going upstairs in the air.
While it is serviced in the giant purpose-built hangar, technician Charlie Jackson has the chance for a detailed examination of the engines that power the monster plane.
The A380 has 4 huge engines, 70,000 pounds of thrust each, full of new technologies. It's one of the most advanced engines that's available on the market today.
These 4 specially developed mighty GP7200 turbofan jet engines are amongst the most powerful ever built. Each draws in enough air to inflate a hot air balloon every 3 seconds. And is nearly 50 times more powerful than Whittle's first turbojets. But in the modern world, its designers faced challenges that were about more than just power.
The main difficulty is to define an engine that is powerful, that gives economy to the airlines, and reduce noise.
Thanks to state-of-the-art design, The A380 burns 22% less fuel per seat than the average 747 jumbo.
These fan blades have been designed specially for this aircraft. They have a very revolutionary new shape to increase the airflow through the engine. 70% of the thrust from the engine actually comes from these blades, and not from the motor itself, which is burning the fuel and turning these blades.
Each of the 24 hollow titanium blades are boomerang-shaped, with a reversed sweep at the tip. This shape slows the air from supersonic to subsonic speeds, not only making the A380 more fuel-efficient per passenger than a family car, but also making it substantially quieter.
This aircraft is well below the limits of noise for the size of the aircraft. He's setting the standard.
But in creating this super jumbo, the team faced yet more challenges and would need to draw on history's engineering trailblazers.
If the whole airplane had been made from the traditional aluminum, it would have been catastrophic to the design.
To achieve more impossible engineering. The Airbus A380 is the biggest passenger airliner ever built. Capable of singular flights of nearly 16,000 kilometers, it is a triumph of aerospace engineering.
Getting an aircraft of this size off the ground to fly practically halfway around the world is an engineering feat.
The aircraft's huge range is mind-boggling, but it also provides designers with a challenge. The A380 would be capable of flying from Dallas to Sydney non-stop. And gigantic journeys require extra provisions for passenger comfort. Its 2 passenger decks provide a total area of 550 square meters, equivalent to 3 tennis courts. At a high-tech hangar in Paris, this Airbus is being stripped back as part of a scheduled service, revealing its engineering secrets.
It's quite impressive to fly on this aircraft. As you can see, it's a very long aircraft. In the business class, you have 80 seats. That's quite important.
But designing for comfort isn't new. In fact, one of aerospace's earliest and most successful innovators set the benchmark. The early aviators who took to the skies had little choice but to wrap up warm and brave the elements. But one man had other ideas. In 1913, brilliant Russian engineer Igor Sikorsky conceived the Ilya Muromets, a plane engineered for luxury travel and the world's first airliner. By using a wind-driven generator and running pipes of hot air from the engine through the saloon, there was electricity and heating, a bedroom, toilet, and comfy seats. 16 passengers could travel up to 600 kilometers in style. With the onset of the First World War, after only 1 year in service, the aircraft was redesigned as a bomber. But the legacy of the Ilya Muromets opened a new world of aviation possibilities. Capable of carrying hundreds of passengers in supreme comfort, over almost 16,000 kilometers, the A380 has redefined long-haul travel.
When you see at the aircraft outside, it's so big that when you come in, when you have a seat, you can imagine how loud it's going to be when it's going to take off. But in fact, no, it's quiet, and you don't even know you're in the air.
Transporting 500 plus passengers in comfort and safety is about more than just chilling champagne to the correct temperature. Flying at almost 1,000 kilometers per hour and nearly 4 kilometers high, with little more than a few centimeters between passengers and Mother Nature outside, posed the designers of the A380 a seemingly impossible challenge.
The forces that an airplane are subjected to on any flight are severe because it's having to expand, it's having to contract, it's having to deal with extreme temperatures. Even the aircraft is actually getting torsional effects on itself while it's flying through turbulent situations.
Since the 1920s, aluminium has been the material of choice for aircraft skins. It's flexible, strong, and light. But when you've set yourself the challenge of building the largest commercial airliner in the world, on which the paint alone weighs half a ton, every single gram counts.
If the whole airplane had been made from the traditional aluminum, it would have been catastrophic to the design. It would be way too heavy. They would have had to have bigger engines, they would have had to have bigger wings, it would have burned a heck of a lot more fuel, and it wouldn't fly very far.
Decreasing the weight by reducing the thickness of the aluminium skin simply wasn't an option, as engineer Ben Evans demonstrates in his lab at Swansea University.
So this gun is going to fire these baseballs at high speed at our target in the stand, and we'll find out how much damage they do.
The aluminium sheet is approximately half the thickness of a traditional aircraft skin.
Wow, let's have a look and see what's happened. And there's the damage. It's deformed this by a good 5 centimeters or so. So really quite a lot of damage with that impact on the aluminium sample.
The designers of the A380 needed a solution that was at least as strong as traditional aluminium, but lighter.
They needed to find materials that could create such a large aircraft that wouldn't weigh like a tank.
Solving this engineering conundrum would be impossible without the great innovators of the past. In the 1930s, American engineer Virginius E. Clark created a brand new alternative to aluminium. Birchboard was impregnated with phenolic resin and laminated under extreme heat. The resulting material he called Duramold. Used in Howard Hughes' famously enormous Spruce Goose seaplane, it was one of the earliest and most successful examples of an aviation composite.
Composites are made up of more than one material and take advantage of the best of both worlds. What we're going to do to prove this is the case is impact test a composite.
This composite is a woven carbon fibre impregnated with epoxy resin, the same dimensions as the thin aluminium Ben tested earlier.
Woo! Literally nothing. So that impacted right here, bang in the middle. In fact, there is absolutely no sign that any damage has been done. So these are the results. This is the composite, this is the aluminium, the same impact force, but look at the damage on the aluminium. So that is a result for the composite. A lighter material and a stronger material. And that is why this stuff is being used by aerospace engineers today.
To build the world's largest passenger plane, engineers would take Virginius Clark's innovations with composites to the next level. and create a brand new material for the A380. Made up of thinner than usual aluminium reinforced with glass fibre, they called it Glare.
The composite materials that make up this aircraft, they're as strong as the traditional materials, and they're as flexible as the traditional materials as well. To give an example of how sturdy they are, there's more than 1 ton of air pushed inside this aircraft when it's flying, when it's pressurized.
Using composites saved 15 tons on the overall weight, making this seemingly impossible aircraft possible.
If they hadn't used Glare or a similar composite, the aircraft that we have today probably wouldn't exist.
It's not just the materials on the A380 that make it stand out from the crowd. Even the method of construction breaks the mold. Sections are built in factories in France, Germany, the UK and Spain before being transported to Toulouse for assembly. The transportation alone required specially commissioned ships and the use of Airbus's improbable-looking A300-600 ST or Beluga super transporter plane. Each A380 contains 4 million individual components, which, once assembled, create an airliner of record-breaking proportions.
I guess this aircraft makes everybody dream when you see it. When people are waiting to go inside the aircraft, you can see children looking at it. People are really excited.
But to make this monster machine flyable, its designers would yet again have to turn to the great innovators of the past.
Often in engineering, the simple solutions are the best solutions.
To produce even more impossible engineering. The Airbus A380 is one of the most technologically advanced commercial airliners in the world.
The technologies used in the design of this machine were not existing 20 years ago.
But for its designers, redefining the terms of modern aviation would mean overcoming some seemingly impossible engineering conundrums.
They told everybody in the world that they will build the biggest aircraft in the world, so it was quite a challenge for them.
And one of the biggest challenges directly relates to the plane's size. Calculations revealed that the ideal, most efficient wingspan for this massive aircraft would be 82.5 meters. But aviation rules state that all planes should be able to fit into an 80-meter box. If the wingspan couldn't be reduced, the A380 would be incompatible with all the world's airports. The answer would lie in one of the great aircraft innovations of the 1970s. In 1973, the world was entering an oil crisis. An embargo on sales to the West saw prices quadruple overnight. And the aviation industry was paying the price. As Dr. Ben Evans demonstrates, traditional wing design has its drawbacks.
Aerodynamicists are always trying to improve the efficiency of wings, which really means trying to improve the ratio of the lift to the drag of the wing. One of the things that was causing a lot of drag and dropping the lift on the wing was what's called a wingtip vortex.
The wind tunnel is simulating an ordinary wing traveling through the air at a typical cruising speed.
In the central section of the wing, you can see that the smoke is very smooth until it reaches the tip of the wing. And once we're at the tip of the wing, you can see this vortex pattern forming.
A wingtip vortex is caused when high-pressure air under the wing spills upwards at the tip to meet low-pressure air above. This creates turbulence and therefore drag, forcing the engine to work harder. The 1970s fuel crisis meant a solution was needed, and aeronautical engineer Richard Whitcomb, working on NASA's Aircraft Energy Efficiency Program, found one. Whitcomb suggested that by changing the design of an aircraft's wingtips into vertical winglets, they would create less drag and burn less fuel.
As I move the smoke trace towards the end of the wing this time, instead of having the single strong vortex that we saw in the case without the winglets, what's happening now is that the flow is smearing out almost into a sheet, making the wing more efficient.
Adding a winglet prevents the mixing of the two airflows above and below the wing, reducing the vortex. The A380 has specially designed arrow-shaped winglets called wingtip fences. And they allow the wingspan to be reduced to just under the maximum 80 meters without compromising the aircraft's efficiency.
Without those design features, this aircraft would be way too big, it wouldn't be practical, and it wouldn't exist today.
Despite its aerodynamic efficiencies, the A380 is still enormous. So how could its creators make it possible for pilots to control this mighty beast, which, fully laden with fuel and passengers, weighs a staggering 560 tons? Once upon a time, it would have been an impossible dream. By the 1960s, the age of the jet was in full swing. Transcontinental travel had never been easier or faster. But a group of audacious Anglo-French engineers thought it was possible to go even faster. To create a supersonic passenger jet.
There were a lot of engineers who said, well, this isn't possible. What you're proposing here is just too ambitious. The result of the work of those pioneering engineers is this, Concorde.
Launched in 1969, Concorde could reach speeds of over 2,000 kilometers per hour. More than twice the speed of sound. Flight times between New York and London were cut in half. But flying this futuristic jet airliner would be virtually impossible using traditional aircraft controls. Concorde would need an innovative new system known as fly-by-wire. At a simulator at Brooklands Air Museum, former Chief Concorde pilot Mike Bannister explains.
You could fly at 1,350 miles an hour, faster than a rifle bullet. Concorde wouldn't have been possible without fly-by-wire because some of the control forces at certain flight conditions really would have been huge.
What exactly is fly-by-wire?
Fly-by-wire is computers telling systems what I want to do. On a conventional airplane, when I want to turn left, I do that, and some pulleys and wheels and cables move the controls. On this airplane, when I want to turn, I do that. It tells a computer that tells the controls what to do. That means the airplane's far more responsive, it can be far more efficient, and is capable of being flown by ordinary human beings.
Concorde was the first commercial jet to adopt the technology.
What did it feel like to fly the real Concorde?
The airplane's a delight to fly. It's like a thoroughbred racehorse rather than a riding school hack, or a sports car rather than a truck. It is so responsive. You can fly it with your fingertips, so why don't you have a go? Very nice. Keep it coming, that's perfect. Right through the bridge. London Assembly Building to the left, a Shard to the left. Fabulous.
Well, Concorde clearly is a remarkable aircraft. Not only is its exterior breathtakingly beautiful, but underneath the skin there is some technology that really revolutionised the aviation landscape and has made what we can do with modern aircraft today possible.
Since its first application on a commercial airliner, fly-by-wire systems have become industry standard. And on board the A380, a highly sophisticated digital system makes flying this super jumbo possible.
For an aircraft the size of this aircraft is relatively a simple aircraft to operate. For flying, the aircraft is here, and it is completely electronic. I mean, there's no cables. It's all generating electrical inputs, which are sent to a computer, which then send the signal onto the flight control surfaces to move.
Spanning some 13 years, the design and development of the Airbus A380 ranks as one of the aviation industry's greatest achievements. Now the A380 is operated by airlines across the globe, and one takes off and lands every 4 minutes. By drawing on the innovations of the past, adapting, improving them, and making groundbreaking innovations of their own, aerospace engineers overcame extraordinary obstacles and succeeded in making the impossible possible.
It was quite difficult to imagine 20 years ago that kind of machine you have here was going to exist, but it's now reality. So what about the future? Who knows? Maybe going to the space with an aircraft.